Good afternoon, everyone. Thanks for coming. Today's presentation is on the NeXtRAD project, and it's an update about the recent progress of each of the sub-projects within this greater project in itself. So I'll introduce you to what NeXtRAD is, in case you aren't unaware of that yet, which I hope most people in the room are. Talk about the previous system very briefly, NetRAD, and then focus on these key components of the NeXtRAD system that we've been evaluating or developing right now in collaboration with the University of Cape Town. So I'll be talking about the RF side of things, the digital backend, the ADC, the DAC, and the programming of all of that. Then look at the clocks that we're using to provide the LO for each of the multistatic nodes, the antennas that are being developed both here at UCL and at UCT, and then discuss what we'd like to do with this once everything is online and working. So NeXtRAD is the new multistatic radar that we're developing here at UCL in collaboration with the University of Cape Town, as I've said. It's a very large project, it's complicated, and has a number of sponsors and collaborators from different countries. We work with Cape Town University, we work with FFI in Norway, we collaborate with O&R Global in the US, and various other parties. As part of this project, there's many sub-projects which are being kind of run not independently, but run by different individuals. The antennas, the digital side, the RF side of things. So I'm going to give you kind of a wide overview of everything, not too deep on each part of the project, but just an update as to what the situation is on each one. And this is because me and Francesco visited Cape Town University prior to the conference in Johannesburg, the radar conference there. And as part of that time, we met with the researchers there and got an update and contributed towards the development of the system. And there's a picture of the UCT campus there with the table mounted in the background. So NetRAD, as we all know and love, I've told you about many times, is an S-band radar that was developed here at UCL. It's been in development and it started back in 2003, and through its life cycle, and this time it's been upgraded from a low power cable system to a high power wireless baseline system to achieve long baseline C cluster measurements. And then in this period here, me and my colleague Francesco have done some experiments with it, looking at human microdoppler, drone detection, wind turbine detection as well. So it's a real combination of measurements that have been achieved. And we're now looking at the handover to the NeXtRAD project, which will again go many years in the future, no doubt, once we've got that operational. And this is why we do it. Multistatics are one of the key things that UCL lead globally on in the radar domain. And we like to measure things in this multistatic networked way and look at the advantage of what multistatic radars bring to the table compared to a monostatic radar, or even several monostatic radars that aren't coherently working together. And this is a typical configuration that we measure our target of choice, which I've said is varied between people, drones, wind turbines, and birds, actually, which we'll be looking at shortly. These are some of the advantages of multistatic radar that are often mentioned in terms of different cluster properties which can be used to your advantage, potential counter-stealth capabilities because signals aren't reflected back to their origin, but that doesn't matter if you've got multiple nodes. The multiple perspectives on targets, improved classification accuracy, which we've proven through numerous publications of recent. Data fusion opportunities where we'll be able to collaborate with people such as Fraunhofer, which are leaders on that kind of domain, and we have the real-world sensor that can contribute to that research. But our goal is to quantify these advantages with real numbers, how better is the classifier, how better is your SNR, how more efficient is your track maintenance, and that's our goal with a real-world sensor. The NeXtRAD system will be an upgrade from the NetRAD system in a number of ways. It's dual band, L and X. It's dual frequency. It's dual polarization, X band. So we'll be able to measure simultaneous H and V signatures in the crossfolds, or in a pulse-to-pulse way. Higher power in some instances, compared to the high-power S-band version of NeXtRAD. And once we have the model of being able to develop a single node, this is scalable to multiple nodes and not limited to just 3 by its nature.
What do you transmit on X-band as far as the pole, the pole?
So we only have a single X-band high-power amplifier currently.
Yeah.
And so we will be looking to, in the initial stages, transmit a single polarization and measure that and cross.
Okay, so you can do either vertical or horizontal.
And then in the future, we'd look to obtain a high-power solid-state switch, which would allow us to go HV, pulse to pulse on the transmit side of things. So that would give us
full.
Yeah. But we're gonna walk before we run, and we're limited by the single HPA.
Yeah.
But that's the goal of Clayton, absolutely. So this is the NeXtRAD architecture, kind of block diagram, I would say, of what we're looking at now. It's changed a bit since we first sketched this up. It's going to be a command and control PC controlling multiple nodes, and then within each node there is a single CPU, the Linux run computer. And the digital side of things is this Pentec card, which is, I'll go into after the RF, but that's our ADC and DAC, which generates our signals and digitizes them. Then the Rhino board, which is a open source FPGA board, is going to be used to generate our PRF and trigger signals and provide them to both the Pentec and the radar transceiver itself. The radar transceiver was a professionally built unit from a South African company, Roytech, and I'll be mentioning that next. As part of clocking the system, one of the key fundamental issues with multistatic systems is the synchronization. To allow you to be coherent with multiple radars, you need to receive a coherent signal, so knowing exactly when it's transmitted and maintaining phase. To do that at multiple sites wirelessly, we achieved that doing GPS discipline oscillators with a bespoke designed units from the University of Cape Town. We've now bought COTS units off the shelf here at UCL, and Jaraz, along with me and Francesco, are evaluating the suitability of those and looking about doing some initial experiments, integrating them into a NeXtRAD system to see how suitable they are, and then also apply them to the NeXtRAD radar. But they also have atomic oscillators within them, and that brings another variable that we can investigate in terms of free running and how long we can maintain coherence. These are our 2 single HPAs that we have, and it will go to an antenna mount, which will be mechanically steered, but over a remote network, allowing us to point to long lap coordinates. The REC system, as it's named, is our big RF box, and that was the item that was purchased from Roytech. That that system is a rack-mounted unit that mixes our signals from the given IF frequency, which is 125 megahertz, up to either X or L band, and then there's our receiver, and mixes that down to the same IF level, which is 125 megahertz. There's some block diagrams of it here, and then here's an image of it on the shelf in the University of Cape Town laboratory. The inputs, again, this requires a 100 megahertz LO clock, which in our initial testing was just from a signal generator unit, a desktop thing, whereas in the real deployment will be provided by a GPS discipline oscillator or an atomic clock source. It has attenuator control, which either can be configured over the Ethernet port or from the BCD inputs. That BCD input is used to tune whether you choose X or L, so it's not simultaneously both, it's either X or L, and then tune the frequency within that X or L band. So our central frequencies by default will be 1.3 gigahertz at L and 8.5 at X, but we do have movement within those bands themselves.
Can you do it pulse to pulse?
That's what we're looking to do as well, and there's been the project with the Rhino board and the integration of the Rhino controlling the REX board has shown pulse to pulse pulse switching of these frequencies and measuring the delays of each part of that to see what P or Fs are achievable when we do that. The IF signal, which is your chirp that you want to transmit, is the final input there, and that's defined by the digital system. Rex is then set up in that mode, and there's no other configuration needed, and the signals just simply pass through that and are mixed up to the required frequencies and then pushed through the high power amplifiers. These are then transmitted and then received back and then mixed down again to this IF frequency of 125 megahertz, as well as some built-in test output statuses. So as part of a professionally produced bit of hardware, that's some of the typical things that you would get from that kind of hardware, telling you the status of things and whether there's any failures within it, which is a good benefit to have. So from some of the early testings of that Rex unit on standalone on itself, we put through a sweeping signal across the bandwidth of the 125 megahertz from 100 to 150, which is our 50 megahertz bandwidth we have. Here we have the signal gen output with a max hold on the spectrum analyzer. And if you ignore the absolute levels of these two received outputs from the Rex unit, because we use different attenuation levels, so the absolute power isn't the important thing here, it's more the spectral shape. You can see that the signal was successfully transmitted through the Rex unit itself, but there was a roll-off seen across the band. And this does happen within RF systems in terms of the higher frequencies are attenuated more. And we measured this to be about 4.4 at the L band, which is the red line here, and 6.4 from left to right in the X band. And that's simply what we saw in terms of putting it through the Rex system itself. And this is prior to the digitally produced linear FM pulse as well. So we need to see what the produced pulse is. In terms of the signal generator, this was completely flat, but there's that aspect to it as well. And the combination of both might produce a significant roll-off that we will need to investigate. Another part of the RF is some of the bandpass filters that are being produced at the University of Cape Town. Here we have the L and X band bandpass filters. The X band was being tested whilst we were in Cape Town. This one has a number of tuning screws here to ensure that it's set across the correct range of frequencies that we desire. And this was being tested with one of the VNAs at Cape Town University whilst we were there. There was some manufacturing issues with the sealing of this top lid unit with the base unit. As you can see here, the cavities that the RF signal is going through. So it may have to be remanufactured, but it's always a learning curve for the student who's just first done this.
You may want to have some groove around the edge.
Okay.
And then you on the top side you have some glove. Then you kind of U-shape.
Okay, yeah. So it's
to prevent the leakage.
Into this.
It's
yeah.
not too flat thing. You have a groove and teeth going to prevent the leakage.
Yeah, I think that might be the problem we have right now. There was a miscommunication between the company manufacturing or the engineers manufacturing and the student who was making it, and there was an air gap.
But this industrial stuff, it's an industrial know-how.
Oh yeah, exactly, yeah. So that's a good suggestion though to give to the student for the second iteration of this.
Yeah.
So as part of the radar, you have the RF side and you have the digital side. So the digital side of the NeXtRAD system is this unit here. In the heart of that unit is a Pentec card, and that card has 3 ADCs and 2 DACs. So we're capable of receiving or digitizing both the 2 X band channels and the 1 L band channel. Although in reality, because the Rex unit can only be tuned to either X or L, we would only ever need to digitize 2 X band channels or 1 L band channel in a pulse-to-pulse way. And here we also have the 2 outputs, the DAC outputs. But again, the Rex unit only requires a single IF input, so we'll only be using one of those. But it's nice to have a single card that has all of this capability on that one card. And this card is programmed in C and has some examples that were provided with it in order to run some of the basic capability. so this sits within a chassis that has a computer unit here, which is running on a Fedora Linux, and the Fedora Linux computer has all the C programming and FPGA programming that's required to run the card. And this card is then attached to the IF input of Rex. You transmit into Rex, Rex mixes up to your required frequencies, and then we were doing some loop tests within the lab, and then receiving our same pulse, and then digitizing back into this Pentec card, and evaluating, if we send this, what does it come out if it's just a loop test? Or, what do we see? So, dealing with this digital system, we need to come up with an architecture or a way of how we're going to achieve what our main goal is. And that, we found out the simplest, which isn't very simple, way to do this is we have a 200 megasample capability in our digitization. But that means the Nyquist of 200 megasamples per second is 100, or 200 megahertz is 100. But our signal runs from 100 to 150. So what we do is actually set our sampling to 180 megasamples per second, which produces a Nyquist value at 90. And that will fold our 100 to 150 signal over to 30 to 80. So when we digitize the signal, it will appear to sit between 30 megahertz and 80 megahertz. And then as part of this card, we have digital up mixing and digital down mixing within it. And with our digital down mixing, we will be able to zero center the output signal so that it straddles 0 hertz and goes from minus 25 hertz to megahertz to 25 megahertz. And this might be explained best in a diagram. So we input our pulse or our chirp, and it has 50 megahertz bandwidth sitting at 70 megahertz. We tune our up conversion frequency to 55, and therefore 70 plus 55 gives our central frequency of 125. And this is what goes into that Rex unit, and that's what we transmit. This comes back in the same form, hopefully, with some delay. And because of the Nyquist folding as I was describing, it will appear to sit at this location. And as the digital up converter and down converter run on the same clock, this dotted line will then push, mix with this signal and push it down to this zero-centered chirp that we end up in our digital signal that we digitize. You kind of start this end and say, I want this, and then work out where you have to set this line, and then work out what you have to actually input, and that's the best way to do it. So from that, we've done some testing with the device and looked to see if what happens if we set all those settings. And that took some time, some learning curve in terms of operation of this system and getting things working. But here's a result showing one of our LFM chirps centered at our 125 megahertz frequency that has been upmixed using the digital up converter within the Pentec system. Now you'll notice a couple of things here. There isn't one signal, and it's a bit messy because there's multiples of these signals. Well, that's because the digital DAC is working at a 360, which is double the ADC, and that has a Nyquist value of heat at this location. So therefore, this generated signal has an image on this side, and you can see a roll-off, which is characteristically digital units. And then this component of the signal here, we're not as confident in terms of the origins of that, but it is, as I was saying, the original signal you input is then mixed up to this 125 megahertz location, and this seems to be sitting at where the original signal was input to the unit prior to up conversion. So it may be linked to that. So this is what you observe. You just do a loop test with the Pentec card itself, not using the RF system. Also, the Pentec has inbuilt capability of inverse sync weightings, which can increase the amplitude to the higher end of the frequencies. So you see this red curve, it has those weightings not turned on. And when you turn them on, that actually compensates for the loss or roll-off within the band to try and reduce some of that spectral roll-off that we were seeing. Now, luckily, when you put that signal, when it comes out of the Pentec, goes through the Rex RF mixing device, you can do a loop test at RF, not at this, just at IF. The Rex unit itself is working as a bandpass filter, and you lose all of those images that I just showed you in that previous slide. And what you end up with is just your chirp at the correct location. Now, this does have the additional roll-off due to Rex and Pentec combined, but this is a very early result with it, and there's further optimizations, and I think the cables and connectors that are being used were not optimal for those higher frequencies. So the student performing the measurement wasn't aware of that, and we're going back with some second iterations of these tests to improve what on this first result. But it's good in the way that at that loop test at IF, you're seeing all of these images that are unwanted, but you're never going to do, the radar is never going to be on IF alone. So you will always be pushing it through that Rex unit. So that removes all those problems, and we've paid for that Rex unit, and that helped us because we get all this bandpass filtering. It does have the spectral shape issue that we need to investigate further, though, and I've said that already. We'll see what happens.
I suppose the issue is, what effect does that have on the, we'll call it the point target response, the cyclodes and so on?
Yeah.
And if you've got a sort of symmetrical roll-off to the spectrum, that might not be a bad thing.
Yeah, okay. Yeah, as
There'll
part of this.
be a loss associated with it, of a small number of dBs.
Yeah.
But the big issue is, what does the point target response look like?
Yeah, we need to look at the match filter response of the signal as well, after putting it through our.
Well, we may decide not strictly to match filter it. There may be some further tapering to be done there, which would improve it.
Yeah, I think another part of the compensation which Francesco brought up was perhaps putting a higher weighting on the higher amplitude components of the signal in your generated chirp in the first place.
Yeah, well, except that means the power amplifier isn't acting at a constant level throughout the pulse.
Right, okay.
Which we might, because it's a Class C amplifier, we probably do want it to.
Okay, so it might be that technique might be limited by the PA.
I think so, yes.
Okay. There is other options. I think there's 3 or 4 suggested. So we'll look into each of those.
Have you measured the characteristic of individual components, the PA, in the gain? You check how flat the gain is, the filter, what the response of these filters. So I think you need to measure every
Each
single
part
component,
of the system,
especially in the high power level.
Yeah.
Because low power signal and high power signal, that the device will behave
Different ball game. Yeah.
The temperature, basically the temperature.
All of this was the low power testing. The high power units themselves were tested by Adrian Stevens, who's doing his master's project on them. And he's built some of the RF front end around those high power amplifiers. They're currently back in the UK in our lab now, and they'll be shipped back to Cape Town for further testing. But you're absolutely right, we need to know independent components of everything and look before we look at the combination. Here we're kind of evaluating the digital solely, and what does that look like solely, and then the combination of the digital and the RF low power.
Although maybe at the end of the day, those roll-off may not be very significant.
Yeah.
You combine them, but you know what each component working will help you to identify the problem later.
Yeah, absolutely. Yeah, these are the stages we're progressing through. Absolutely. So another part of the system is this Rhino board, which I mentioned previously, and we were hoping to originally digitize with this system, but the task of this is now adapted to being the PRF generation and the trigger generation of the system. So this works in collaboration with the Pentec board and provides the PRF at kilohertz, 5 kilohertz, 10 kilohertz, as triggering to that and distributing that. And this has been programmed by in VHDL code, and that part of the system is operational right now. A user interface or a combination of a control of that via a greater GUI, which controls the radar as an overall system, needs to be completed. But as a standalone unit, it's capable of doing that right now. Now on to the clocks. The Cape Town clock is shown on the left, and the UCL clock is shown on the right. The Cape Town clock were in-house developed by Stefan Sandenberg, and this was a few years ago now, and probably before it was readily available to purchase such units. And that allowed us to do these wireless measurements, and it was a great achievement, this combination of UCL and UCT, and helped us a lot. They provided both 100 megahertz and a trigger because there was an FPGA within that system in itself. Off the shelf, what we purchased was an atomic clock and a GPS diode, and that provides 100 megahertz and a 1 PPS, 1 pulse per second. But it doesn't have any triggering capability, and it doesn't have any, apart from some tuning and synchronization, it doesn't have any configurations such as the custom-built Cape Town units. But it's a more modern unit that has a higher specification, and it has, because of the atomic clock oscillator internally, we have this potential to run free running mode without GPS in case GPS is denied or jammed, to see what the capability of the radar is in a GPS jammed scenario. So this is an image Jairus is working on right now in terms of, here's two of these clocks here, and we're looking to measure the relative phase between them, looking to input them into an analog devices evaluation board and produce a 100 megahertz signal. The default is 10. And that signal also doesn't need to be a sine, we require an LV Peckel signal in terms of injecting that into NeXtRAD. So this is an ongoing project, and it's very interesting. Hopefully we'll get some good results out of this soon. Now antennas. This is not exactly my field, but I'll give a brief overview of each one that's currently being developed. So there's some developments happening in Cape Town University as well as UCL. Here's one of the examples of this pillbox antenna, which was produced at Cape Town with this kind of paint tin, circularly polarized end feed. And this was tested on the roof of the Cape Town University. But as you can see, it's a big antenna. And typically we'd like to use this.
You can't see, you have no
Yeah. It's a big antenna.
You should put your feet there, that's how big it is.
Absolutely. There's a man standing here. No, it's a big antenna, and because it's solid metal, the windage on it will be quite high.
I reckon, do you mean that the one below is a CP antenna?
It has two feeds here.
Circular polarization.
Dual CP or dual polarization?
Dual.
I think it's that feed that was on it.
No, the aperture is rectangular.
I think it's dual polarized, not circular polarized.
But dual linear,
Yes.
I think that's more likely.
But it should be square then.
But doesn't seem to be like it has the beam width as a square, because it's like rectangular.
It's not the same dimensions.
Yeah.
Absolutely.
You mean dual band as well, doing is not in the same frequency range. Because if you said dual polarization at L band or X band.
No, these will be the L band antennas. They're not dual band.
So that means for L band you don't need dual pro.
We don't in terms of we don't measure H and V. We only have a single channel at L band. But I guess if you had a dual pole antenna, we would simply move the cable rather than rotate the antenna.
It doesn't look like a dual polarization antenna.
Look, it looks that the upper one is the L band and the bottom one is the X band.
I think
both L band.
I think they're both L band.
All L band.
But the bottom one is the asexual antenna. With the highest aperture is on the.
Yeah, but we have these two dimensions, these two apertures, one that orthogonal to each other. So that means the oscillating bit is still this dimension and this dimension. So that means these two sides should be the same
size. It may be an initial prototype that they were testing this dual feed to see what response they get. I don't think these are necessarily that version certainly isn't the final one that we would be using in the field.
But the point is, if you want a dual pro antenna, you don't need a circular feed.
Right. I think they had this concept of these circular feeds, and perhaps they wanted to apply it to an antenna and evaluate the response afterwards. It may have been along those lines, rather than the other way around in terms of what the requirement was.
I think I have seen from QPAR They have a dual polarized horn with a silicon waveguide adapter.
It's like a waveguide. That's like a waveguide with two.
Yeah.
waveforms.
Yeah.
And they were evaluating the isolation between these different ports as part of the antenna work at Cape Town. And then here's another antenna. Yeah, so you've got someone for scale this time. So this is, again, quite a sizable antenna, L-band. It's fed from this kind of paint can arrangement again with this dish here. The dish itself was fairly flat when we were in Cape Town, and they're looking to bend that dish to evaluate change it until you get to the required beam width of what the desired requirements were, which is 10 degrees. Kenneth's shaking his head there, so we'll see what happens with that. But they're doing some tests on the roof between two of the buildings in Cape Town.
It's an off-the-shelf product, right? It looks like it is.
Yeah, I think
This grid looks like it is, but this internal bit isn't, and this paint can isn't, and this is just a wooden stick.
What's the pay cap for?
That's where the feed is here, so the feed goes in here.
Why is it a paint can?
I think it's similar to this previous waveguide. They were using. They seem to want to use that as one of their feeds into the dishes.
Okay. The offset is no, it's not offset. No, it's not offset.
No, it seems centrally within that dish. So some of the results from
If
this.
they want to get it right, they need to know how the beam come up with the tin can.
In terms of coming out of that
Yes.
tin can feed, yeah.
Yeah, so you need to measure the angular response of that tin can. Then you design that curvature to cover.
To match that.
To
Cover the tin
minus
dB.
10 dB
Yeah, 10 dB.
angle.
They at Cape Town, I don't believe that they have an anechoic chamber though, so they might have some difficulties measuring solely from that paint.
I remember
that
when
paint
we-
Or
can.
actually, you can, for this kind of simple geometry, you can model it.
Modeling it from out of that paint can, yes.
Because you need the tin can, the radiation pattern will be y.
Mm-hmm.
So that means you need to have very large reflector to enclose that.
To
cover
capture all that energy. Yeah.
To get you to the beam.
Yeah.
So that means that's why I shake my head with you, say you flip it and bang it to get to
It might change significantly, yeah.
Yeah.
Yeah, they don't have chamber, so when
But they do have the advantage of a point-to-point rooftop measurements
Yeah.
that they're capable
I
of
think
doing
if
over
for the
free
radar
space
master program, we had to go to Stellenbosch University
to see
get
the
chamber.
chamber.
I think for student projects, fine. I think we will receive something anyhow.
Yeah,
We will
yeah,
receive
yeah.
something, but does it match or provide what you want? It's not
That's
that
another
straightforward.
requirement. Absolutely. Well, let's see. I think the early results from those tests will be coming
I think for
out
fun,
shortly.
that's fine.
Yeah. Okay, on to a subject Saad can comment on. Any questions, please pass to him. This is the UCL side of the antenna development. So Saad has been developing this slotted waveguide antenna, and he's looking to adapt this also with L-shaped dipoles attached to just adjacent to the waveguide slots, as well as developing an S-band version for this for testing with the NeXtRAD system in the UK. This has a fairly wide azimuthal beam width, but the interesting thing is the capability of stacking multiple of them and narrowing that beam width, and that's something that we're looking to do as part of that project, and I think that'd be really interesting. So as a reminder, all of these parts are sub-components of a greater radar, and it takes a lot of work and a lot of people to bring it all together and get everything operational. And our goals are, with all these novelties of dual pole, dual band, longer range, fully multi-static rather than just bi-static, because we were limited by only 2 clocks for some of the measurements previously, and atomic clocks and GPS diodes, and waveform diversity I didn't mention too much, but the capability of changing your waveforms within that Pentex system. There's a lot of variables and a lot of investigations to be done, so there's a lot of interesting work to happen.
So when you talk about waveform diversity, you
Yes.
think about some work Pierre has been doing in waveform diversity.
I'm meaning more having a library of waveforms within the system and transmitting them and seeing how, for example, C-clutter statistics change with that, or target characteristics change in a multistatic way. And I think that's how I envision the early measurements being done on And then again, some of the things we'd like to measure with the system once we're operational. I think there's plenty of opportunity for good research in this domain. So, overrun a little bit, but I've told you everything about the recent developments with the radar, and said the RF is operational. We have these preliminary results. We've made some good progress recently with the digital side of things as well. There were some delays in some of the X-band antennas at UCT on a part of a small part of a master's project there, but they're now looking to get that outsourced outside. And I mentioned the UCL antennas that we're looking here, and possibly some S-band versions as well. So some of the timescales for low power measurements, we'd like to get some low power tests to the radar. Our first detection, hopefully of table mountain, that's quite significant to spot, before Christmas. And then higher power tests with the high power RF integrated February time. And then going to our first biostatic measurements July time.
Where will you do the high power test?
South Africa.
Okay, better.
Yes. Absolutely.
Not in UCL.
No, not yet. Okay, thank you very much. Any questions?